talking about simple interest in the previous lesson, it was, well, pretty simple to understand. But the problem is, in the real world, most institutions, such as banks or other people that lend money, don't really use simple interest when they calculate interest. They use something called compound interest. You'll see why in a second, but essentially, using compound interest earns them more money than if they simply used simple interest. The main difference between simple interest and compound interest is that for simple interest, you are calculating the amount of interest based on what the initial amount, or the principal, was at the very beginning of the term. So if you put $1,000 into an account and it earns simple interest, let's say 5%, then you're going to calculate 5% of $1,000 every single year for the entire length of the term. Basically $50 a year. If it's compound interest though, what you do is at the end of each compounding period, you adjust the principal. So if the initial amount was $1,000, and then at the end of the first year, $50 of interest was accrued, for the second year, instead of calculating interest on that $1,000, you would now calculate the interest on the $1,000 plus the $50 of interest that you earned in the first year. So now the 5% interest is calculated on $1,050. Well, that's going to end up being more than $50 the next time you calculate interest. And this keeps going and going every single compounding period. That's why compound interest is the preferred method. You earn more money the more and more years the money is in the account. A compounding period just happens to be the time interval after which compound interest is calculated. You'll commonly see compounding periods that are every year, sometimes every month, sometimes every week. We can think of compound interest just like a geometric sequence. In fact, the formula for calculating compound interest is almost identical to that of a geometric sequence. A equals P times 1 plus I to the exponent n. There's some variables that we're using here that we used when we did simple interest, such as the A for the amount and P for the principal. But the things that are missing were the R and the T. We've replaced them with I and N. We use I for the interest rate because we want to differentiate between when we're talking about simple interest and when we're talking about compound interest. So we use R for simple interest and I for compound interest. We also don't use T anymore because the amount of time in years isn't as relevant as the number of times we're going to be compounding the interest. That's more relevant to us. So sometimes the n value will represent years, but sometimes the n value will represent something different, like days or months or weeks or who knows. We'll see some examples. But let's get used to thinking about things in terms of the number of compounding periods instead of in years. Alright, let's start with an example. Helga wants to purchase a new guitar. She borrows $650 from her bank, and then she plans on repaying the bank in 5 years. The bank has decided to charge her 12% per annum, remember that just means per year, compounded annually. So when you see compounded annually, the first thing is that this isn't simple interest, it's compound interest. And because it's compounded annually, that means that each compounding period is 1 year. So at the end of every year, we're going to readjust the principal to a new amount. So here's part A. Determine the amount that Helga must repay after the 5 years. Well, we've been told what the formula was for compound interest. Compound interest is equal to, the amount, I guess, after the term is equal to P times 1 plus I to the exponent n. The P is our principal, so our principal was $650. I was our interest rate calculated on a yearly basis. So because this is 12% per year, our interest rate is 12%, or 0.12. Inside the brackets, though, we're going to write it as 1 plus 0.12, so I guess we'll write 1.12. And now the number of compounding periods, Well, because she's repaying after 5 years, and we compound every year, well, every year for 5 years is just equal to 5. So in this case, n does equal the number of years, 5. Well, let's plug these numbers into our calculator. 650 times 1.12 to the exponent 5. Remember, bed mass does matter. So 650 times 1.12 to the exponent 5. And we get $1,145.52. $1,145.52. Huh, she only borrowed $650 from the bank, and 5 years from now she needs to repay them $1,145. Yikes. Alright, part B asks, how much interest will she have paid after she's paid that amount back? Well, this seems pretty obvious, but let's just make sure we understand what we're asking. Her principal, or the amount that she borrowed, was $650. She's paying the bank back $1,145.52. So whatever the difference is between those two amounts, that's the amount that was interest, or the fee that she paid for borrowing that amount. So the amount of interest is just going to equal the amount that she pays back, subtract her initial principal. You can think of it like this. I don't usually write the formula down because this is just, common sense. The interest is going to equal $1,145.52 minus her initial amount that she borrowed from the bank. So you can do this in your head if you can, or if you can't, just pull out your trusty calculator. 1145.52 subtract 650. We get $495.52 in interest. Now let's compare this to the amount of interest she would have had to pay if the bank instead charged simple interest rather than compound interest. So what's the difference? Do you think that she would have had to pay more interest, the same amount of interest, or less interest? Pause the video and think. Alright, well let's recall what the interest formula was for simple interest. Remember, interest for simple interest was I equals PRT, principal times the rate of interest times time. Well, our principal was $650. The rate of interest is 12%, and the amount of time in years was 5, so 5 years. So we'll plug 650 times 0.12 times 5 into our calculator. 650 times 0.12 times 5. That's $390. Far less than the $495 she paid because she used compound interest. The bank sure is smart. $390. If questions were all like that, then compound interest would be a pretty simple process. However, in the real world, it's not quite as easy. What we can do with compound interest is we can vary how often the money is compounded. It's not necessarily compounded every single year. So banks and other institutions use different compounding periods other than annually. A lot of times you'll see semi-annually, which means twice a year, quarterly, monthly, and I even mentioned that sometimes they'll use weekly or even daily. So when we change the compounding period, two different things in our formula will be affected: the I value and the N value. The P value, your principal, stays the same. That's just the amount of money that you initially put in. The A value, well, that's going to change depending on what your I and what your N is. But the I and the N both change. So let's take a look at this example in the yellow box. We're going to invest money into an account that earns interest at a rate of 8% per annum for 3 years, but compounded quarterly. So quarterly means that we're paying 4 times a year. Let's see how the N changes. So if n represents the number of compounding periods, we now need to consider, all right, instead of n being number of years, it's how many times being compounded. Well, because it's going to be in the account for 3 years, and each year we're compounding 4 times, that's a total of 12 compounding periods. 3 years times 4 periods per year. So when we plug in into our formula, we're going to use n equals 12, not 3. Now let's see how the I changes. Remember, I represents your annual rate of interest, or how much that you're going to charge for interest over the entire year. But because we're compounding quarterly, it's not fair to take our annual rate of interest, 8%, and use that each time we compound in the year. That's way too much interest. That totals, a total of 8 times 4, or 32% interest per year. We don't want that. So what we're going to do is we're going to take that 8% and divide it evenly over the year, or over the number of compounding periods. So each compounding period, instead of charging 8%, will only charge 8 divided by 4, or 2% per quarter. So our interest rate we're going to use in our formula is 0.02, which is just 8% divided by 4. Well, let's revisit Helga and see how changing the compounding periods affects the amount that she'll need to pay the bank. So we're going to see what happens if we compound semi-annually and what happens when we compound monthly. Remember, Helga borrowed $650 at 12% per year for 5 years. So let's compound semi-annually. So first of all, we need to figure out our new n value. Remember, our n value is the number of compounding periods. Semi-annually means twice a year. So twice a year for 5 total years would be 2 times 5, which is 10. So our n value is going to equal 10, twice a year for 5 years. The interest rate, remember, is 12% per year, but because we're compounding twice a year, we need to split that 12% evenly over the compounding periods. So that 12% per year will have to be divided into 2, because we're doing it twice a year. So the interest rate we're going to use in our formula is 6%. Remember, we'll write that as 0.06. Well, now let's plug it into our formula. The amount equals p times 1 plus I to the exponent n. Her principal was $650. The interest rate is 6%, so 1 plus 6% is 1.06. And the number of compounding periods was 10. Plug this into our calculator. We get 650 times 1.06 to the exponent 10. $1,164.05. So $11.64.05. Do you remember how much it was before when we only had to compound annually? It was $11.45. Well, this is $11.64.05. More money. It's almost $20 more. Just by changing the amount of times we compound from annually to semi-annually, we're raising the amount of money we need to owe the bank by $20. Alright, so what's going to happen now when we compound monthly? What's your guess? Will we need to pay more or less than the $11.64.05? Well, if you guessed more, I think you're going to be correct. But let's take a look. Again, our n value is the number of compounding periods. So we're compounding monthly, which means every single month for 5 years. How many times is that? Well, every single month is 12 times a year. And we're doing it for 5 years, so that's 60. Our n value will be 60. Our interest rate has to be split or divided evenly over those 12 compounding periods per year. Don't be fooled, it's not divided over the 60 total compounding periods, it's just divided by how many times you compound per year. So because it's 12% annually, but we're compounding 12 times a year, my interest rate is just going to be 1%. And I'll just write that as a decimal right away. So our amount will equal the principal, $650, times our interest rate of 1.01 or 1%, but 60 compounding periods. Our interest rate was higher over here for 10 compounding periods. It's lower, but for 60 compounding periods. We'll see how much of a difference this makes. So 650 times 1.01 to the exponent 60, $1,180.85. That's $16 more than when we compounded semi-annually. This is a lot of extra money the bank's making just by changing their compounding period. And normally banks and other things like credit cards and those types of financial places compound monthly. So you can see that they're going to earn more money compounding monthly than if they just did it semi-annually or annually. All right, let's look at one final example of using compound interest. We're going to determine an interest rate in this question. We have Joe Schmo, and he's starting a toothpick company. He applies for an $8,000 loan at the Skewville Bank, which he plans on repaying in 4 years. Joe is told that the amount he will need to repay in 4 years is $11,501.24. So what rate of interest, compounded annually, is Joe being charged? Well, let's put in our equation here. The amount equals P times 1 plus I to the n. Remember, this is our compound interest formula we're going to keep using, so always write this first in your question. We need to look for the rate of interest, or what the I value is. So we should have values for A, P, and N. He applied for an $8,000 loan, which is the amount that he is starting with. So that's our principal. So our principal is going to be $8,000. The amount he needs to repay at the end is $11,501.24. So that's our A. $11,501.24. The I we don't know, so I'm going to keep this as 1 plus I in the brackets. The number of compounding periods, well, he's going to repay this back in 4 years, and it's compounded annually, which means it's just once per year. So once per year times 4 years is equal to 4. So our n value will be 4. So all we need to do now is isolate for this I. So remember, backwards BEDMAS when isolating. So we don't have any addition or subtraction to this I other than what's in the brackets, but for backwards BEDMAS we do brackets last. So we're going to do our multiplying and dividing. So let's get rid of this 8,000 that's right here. So divide both sides by 8,000. And we end up with 1 plus I to the exponent 4 on the right-hand side. And I'll need my calculator for this one. $11,501.24 divided by 8,000. So that's 1.437655. I'm going to write down the entire thing, 1.437655. It's important to keep all of the decimal places here because we're not done our calculation. I don't want to have a mistake in rounding here because I rounded too early. So I'm going to keep all of my decimal places. If you want, you just keep this in your calculator. Well, now we need to get rid of this exponent 4. So if this was an exponent 2, it would be easy. I would just take the square root. But because it's an exponent 4, instead of taking a square root, we take the 4th root. So I'm going to take the 4th root of both sides. So we just write a little 4 in front of the square root sign there. Okay, so that in essence will cancel out the 4's. But if I want to take the fourth root of 1.437655, on your calculator you're going to use the button that looks like this. So for most people, you will put a 4 into your calculator first, hit this button, that looks like a square root sign with an X in front of it, and then you're going to put the 1.437655. There are some calculators that do this the opposite way, where you put 1.4737655, this button, and then 4, but most of them do it in this order. So let's calculate what that equals and see where we end up. So on our graphing calculator, the button isn't directly right on the calculator, but I'll just type 4, and then we go into the little math button here, and you'll see down option 5 is that X and then the radical sign. So that's the button we're going to use, and then 1.437655. So we end up with 1.09499886667. So we get 1 plus I equals 1.09499, and then basically another 9, rounded. So this looks as though it's 1.095 essentially if we round it. Now if I want I by itself, I'm going to now subtract 1 from both sides. So my interest rate is going to equal this, but subtract 1, so 0.095 when I round it. And so how do we read this? Well, this is equal to 9.5%. Annual compounded interest. So there you have it. You're going to see plenty of examples that use different interest rates, different compounding periods. Some questions will ask you to find the interest rate. Some might even ask you to find the number of compounding periods. That one's a bit tougher. But you're essentially going to be using the compound interest formula, A equals P times 1 plus I to the exponent n, for all of these questions. And you just need to know how to rearrange them. Don't be fooled when it's a different compounding period other than annually. Just change the I and the n values accordingly. Don't stress out too much about these questions. Remember, in the future, this will only be your money you're dealing with. Good luck!